Now I want to go to South America because they have beautiful landscapes. I've never been to South America, but I'm told that they have nice landscapes, at least big mountains, the biggest on Earth. Well, actually, I was testing you. The biggest mountains on Earth are in Asia, if you didn't know that. I suck at geography, but you guys seem to suck more than I do. Hey, so imagine I just arrived in South America, and I want to do a hike in South America, in these mountains. Now, the problem is I've just arrived, so I cannot go very high in elevation, because I would get sick. So I can do only hikes up to a certain elevation. So say I cannot go above these darker areas. Okay, so I do the hike, so I'm here. Well, I don't want to get lost, so what I'm going to do is to take a cable. I'm going to leave one end of the cable at the initial point, and in case I get lost, I can just go back. So I leave one end of the cable where I start, and then I go for the hike. So I walk all around the mountain, enjoying the beautiful view. And then I come back, and when I come back, I have the other end of the cable with me, and I find the end of the cable that I left. So I have two ends of the cables now. I can tie them together. This gives me a loop. Okay, so now I have a loop here, and I want to get the loop back. So I can try to pull on the loop. So I would pull on the loop to get it back. But it would get stuck by the mountain. I wouldn't be able to retract the loop because of the mountain in the middle. So the loop would be non-retractable. Okay. Now this idea of the loop seems like a very simple idea, but it says something very fundamental about the topological properties of this surface here. I cannot retract the loop. I mean, I could if I went above the mountain, but I can't. And that says that there's, in a very topological sense, a hole here in the middle to correspond to the mountain. Now, these sort of loops have been studied by French mathematician Henri Poincaré, and it has really revolutionized the way we think about these spaces. It's one of the greatest ideas of the 20th century. In particular, if you look at this torus, so this torus is actually a deformation of the weird shape I showed earlier, and the connectivity of this torus is actually the same as the connectivity of the weird surface I showed earlier. Okay? Now, on this torus, you can imagine doing hikes. So, for instance, you follow the blue loop and get back to the initial point. Now, if you try to retract the loop you've created, you wouldn't be able to do so. This blue loop is fundamentally non-retractable. Similarly, the red loop is also non-retractable. Now, what's amusing is that the blue loop and the red loop are not the same kind of non-retractability, because you cannot deform the blue loop to obtain the red loop. They are very different. And there are also other loops you can do, like you can do the blue loop and then the red loop. It would give you another loop, which is very different from the two others. In fact, the set of all these loops that you can do really defines a connectivity of this shape. And it's what Poincaré called the fundamental group of the surface. Now, in this case, well, it's a little bit complicated. So Poincaré faced the simplest kind of shape in terms of these loops, which would be a sphere. On a sphere, here, if you go around the sphere, you can do any loop on the sphere. The loop you did would always be retractable. So spaces like that, whose loops are always retractable, they're called simply connected. So the sphere is simply connected. Now, what Poincaré proved is that if you take any surface, for that matter, any surface which is bounded in space and has no edge, so any nice-looking surface, if it is simply connected, then it's because it's a deformation of a sphere. It's very much like a sphere. So basically, in a topological sense, all these shapes which are simply connected, or these surfaces which are simply connected, or more or less a sphere. Now, this idea of loops can be very simply generalized to higher dimensions. And Poincaré then looked at higher dimensions, so after 2, it's 3. So he looked at dimension 3. And so he imagined a 3-dimensional sphere. It's kind of hard to imagine. And he wondered if any 3-dimensional space which is bounded and has no edge is a deformation of the 3-dimensional sphere or not. Well, he didn't really try, but I guess he tried, but he eventually wrote that this problem would take us too far. It's kind of saying, well, it's too difficult for me, and for that matter, it's also too difficult for anyone who would try. I call it self-confidence, but you could also call it arrogance. Well, he's French, so that's understandable. So he kind of stopped here because dimension 3 seems too difficult. And what's amusing with that is that the problem gets simpler in very high dimensions. In fact, it was found, so I'm told. So it was actually first proven for dimensions 6 and higher in the 1950s, and then for dimension 5, and then dimension 4, and then dimension 3 was like the hardest one. It was actually one of the 7 problems of the millennium by the Clay Institute of Mathematics. Now, since then, it's also the only conjecture of these millennium problems which has been proven. It was proven in 2004 by a mathematician named Perelman. Okay. No, so that's very nice because it kind of tells us how we now can understand any surface, any volume, any space of finite dimension, at least in a topological sense. Now, I want to take us further now. And by further, I don't mean to infinity, because infinity is actually rather similar to that. To go further, we will now look at dimensions which are not whole numbers. These shapes, which have dimensions which are not whole numbers, are called fractals.